So section 5.1, duality. Now in this chapter, we are going to study weak topology on Balach space and weak star topology on its dual. But in order to understand these concepts better, we first concentrate on general locally convex spaces for the first two sections. So here, X is a locally convex space, and X star is a dual. For X in script X, X star in script X star, we introduce the notation X, comma X star. This, it looks like inner product, or this way we change the order of X star of X and X. And this inner product like notation stands for X star of X. You know, X star is a linear functional. So actually X star is a function on X. So X star of X is the value of the function X star at the point X. And this is the meaning of this notation. So in general, this X star X, this is not an inner product. We just use the notation of inner product. The meaning of this notation is just the X star of X. So we have this X, comma X star equals this X star, comma X. This is just the X star of X. This is just a notation. So now we are going to define the weak topology. So if X is an LCS, the weak topology on X, denoted by WK or sigma of X, X star. This is just a notation for the topology, okay? This is the topology defined by the family of semi-norms, P's of X star, where X star is in script X star, where P's of X star of X equals absolute value of inner product notation X, comma X star. So so this is the definition of weak topology. Definition of weak topology. And the weak star topology is X star, denoted by WK star, or sigma of X star, comma X, is the topology defined by the family of semi-norms P's of X. X is in script X, where P's of X of X star is defined this way. Right? In the product notation, X comma X star, then we take absolute value. So this is the notation, this is the definition of weak topology and weak star topology. For this topology, we need to clarify several points. The first is that with this topology, we get a space is again, with this weak topology, the space X is again a locally convex space. So in general, X originally has a topology. And this weak star topology is a second topology of X. And we say this second topology, again, with this second topology, the weak topology, X is again a locally convex space. Now we have to recall, we need to recall the definition of locally convex space. Locally convex space, by our definition, is a space with a topology defined by a family of semi-norms. And this family of semi-norms, let's recall that the topology defined by a family of semi-norms. In this topology, each open set is the union of basic open sets. Basic open sets, so we have for each point, we have basic neighborhoods. The basic neighborhood is defined by a finite number of semi-norms. So each basic neighborhood of a point x0 is defined in terms of a finite number of semi-norms. P, J. J is from 1 to k. And this basic neighborhood is the set of X such that Pj of X minus X0 is less than epsilon with epsilon j. Okay, we don't have to the absolute value because semi-norms is automatically non-negative. So open sets, we are talking about topology defined by a family of semi-norms. And each open set is the union of basic open sets or basic neighborhoods of a point x0. So a basic neighborhood of a point x0 is the set of X such that piece of j of X minus X0 is less than epsilon j. J is from 1 to k. Okay. So the topology defined by a family of seminorms this way. By our definition, a locally convex space has a topology defined by a family of seminorms. And we have another condition. The topology defined this way is Hausdorff. And this Hausdorff condition is equivalent to that each non-zero point, for each non-zero point, the point 0 has an open neighborhood which does not contain the given non-zero point. So for each non-zero point is outside of an open neighborhood of 0, is outside some open neighborhood of 0. So this is the condition. This is equivalent to Hausdorff condition. So in the moment, we are going to see that this condition, Hausdorff condition, is satisfied. So that's why X with weak topology is again a locally convex space, as similar for weak star topology. Okay, that's the first point we want to say. The second point about this weak topology is this. After look at this definition, we may have a natural question. This new topology is the same as the original topology, or it should be, or it is different. The answer is this. In general, the weak topology is different from the weak star, from the original topology on X. But for X star, in general, we don't have a fixed topology. So the weak star topology is a topology on X star. So when we are not talking, we don't have a original topology on X star. So we don't say weak star topology is different from the original topology because in general, we don't have an original topology on X star. But if X is a normed space, then X star is a Banach space. So of course, then it has a Banach topology. And in general, this weak star topology is different from whatever topology. In general, the weak star topology is different from whatever topology on X star arises in some way different in general. Okay. Now let me say one more thing about this weak topology in order to get some idea whether the weak topology is the same as or different from the original topology. Let me say the following. If X is finite dimensional, then the weak topology on X is the same as the original topology on X. And it is the same as the Euclidean topology. On the other hand, if X is infinite dimensional, then the weak topology has the following property. Use this property. This property is one of the ways to tell whether the weak topology is the same as original topology. The property is this. If X is infinite dimensional, then each basic neighborhood of a point contains a affine subspace. So the basic neighborhood is unbounded. If the original topology of X does not have this property, then the weak star topology is certainly different from the original topology. Let me say it again. The property is that each basic neighborhood, and hence each open set, non-zero open set, contains a affine subspace, so it is unbounded. So here we are going to have a problem, homework problem number 10. And from the hint, we can see that why this basic neighborhood is unbounded. Okay, it contains a affine subspace, so it is unbounded. So then this might tell us that weak topology is different from the original topology. Okay. So yeah, we need to look at the problem, homework problem number 10 carefully. This tells us that in many situations, weak topology is different from the original topology. Okay, now, so now we are going to see that why this is why the weak topology is Hausdorff. Okay, suppose X is a point in X, and X is non-zero. By theorem 439, this on page 111, 0 and X are strictly separated. So there is an X star in script X star such that X star is non-zero. Thus, this means that the absolute value of this is a semi-null, which separate X from 0. So therefore, this is Hausdorff. And by our definition, this is a locally convex space. For our textbook, the Hausdorff condition is built into the definition. So every locally convex space must be Hausdorff. So then look at weak star topology. Now, if X star is in script X star and X star is not equal to 0, then of course there is an X in script X such that this is not 0. And here, different from the above, we don't need to use any theorem. Just by what we mean by X star is not 0. X star is, as a function is not 0. That means it is non-zero at some point, at least one point. So that's by the meaning of X star non-zero. So there is an X in X such that this is 0. Okay, we don't need any theorem, just by what it means by saying this is non-zero. So this, again, this tells us that weak star topology, X star with this weak star topology is a locally convex space. So we have convinced ourselves that X with weak topology is a locally convex space, and X star with a weak star topology is a locally convex space. Now, let's see that, say something about the relation between original topology and weak topology of X. The original topology of X is defined by all continuous seminorms. So, but weak topology is defined by some continuous seminorms. And these some continuous seminorms are defined in terms of continuous linear functional. So then you take absolute value. These are continuous seminorms. Then these are just some continuous seminorms. They are not necessarily of all continuous seminorms. So this says that the weak topology is contained in the original topology. Or using the language of topology, weak topology is weaker than original topology. And original topology is stronger than the weak topology. Okay. Now, we have theorem 1.2. If X is a locally convex space, then X with weak topology, this new space, as a point set, is the same as is just X, but with another topology, weak topology. And this X with weak topology, this space has a dual. And this dual is the same as original dual. Okay, so this is just saying that so this equal sign here just means they are the same as vector spaces. Here we are not talking about topologies because we don't have an original topology on X star. So we don't have here. This equality is about vector spaces. This dual is the same as the dual of X. Okay, they are same as vector spaces. So now we are going to prove this. Okay, proof. Since every weakly open set is open in the original topology. Yeah, this is exactly what we said earlier about weak topology. Weak topology is weaker than the original topology. Okay, so that means weaker topology means you have this every open set. Weak open set is an open set in the original topology. So a topology is weaker. This means it has fewer open sets. A topology, we say, is stronger, means it has more open sets. So weak topology is weaker than the original topology. So every weakly open set is open in the original topology. So you know that when you have, if a topology is weaker, okay, then a linear function, a linear functional or linear, any function is more difficult to be continuous. Okay, it's more difficult. So it's more difficult to be continuous. So if a linear functional is in this set, that means is continuous with this topology, with weak topology, then it must be continuous with the original topology. Because you remember that continuous means for each open interval, open set in the set of real numbers or complex numbers, the pre-image of each open set is open. Okay. When we have fewer open sets, then this is more difficult for this condition to be satisfied. So if it satisfies this more demanding condition, then it must satisfy less demanding condition. So that's why each f here, if it's continuous here, then it must be continuous here. So each f in this set belongs to X star. Okay. Our goal is to prove these two sets are the same. So each f here belongs to this. That means this is contained in X star. So now we have to prove the reversed inclusion. That means we have to prove a linear functional in X star must belong to this one. Okay. So conversely, suppose that G is in script X star. So we must prove that this G belongs here, belongs to here, okay? So for each epsilon greater than 0, the set is weakly open, is weakly open. Now let's see why it is weakly open. Yeah, this is weakly open because for the weak topology is defined in terms of the seminorms. And the absolute value of which kind of seminorms? The absolute value of G is such a seminorm. So the weak star topology, the weak topology is defined in terms of this seminorms. So that's why this, it is open, it's weakly open. It is weak, it is open in the weak topology. It is open in the weak topology. Okay, this is just because absolute value of G, by the definition, is one of the seminorms defining the weak topology. So this G is weakly continuous at 0. That is just by the condition of continuity. So since this is weakly open, so G is weakly continuous at 0. Then earlier we say that if a linear functional is continuous at 0, then it is continuous everywhere. Earlier we have such a proposition. So therefore, G is in X, comma, is in the dual of X with weak topology. So we have proved this theorem 1.2. I think we stop here. That is for today.